Next, we'll talk briefly about vectors. Vectors are quantities that have both magnitude and direction. Vectors are used frequently in physics, but they also show up in things like graphic design and robotics. A simple example of a vector would be me telling you to take 5 steps to the left, where the magnitude would be 5 steps and the direction would be to the left. We represent them using arrows. So the length of the arrow would tell you the magnitude, and the direction that the arrow is pointing would be the direction. This arrow is a directed line segment, and it has an initial point where we're starting, and the point where we stop is called the terminal point. The notation, a notation that we use to represent vectors, would be using the letters representing the initial point and the terminal point with an arrow above them. You'll also frequently see just a bold lowercase letter to represent a vector. Two vectors are considered equivalent if they have the same magnitude and direction. A vector would have two components. So one would represent the horizontal, one would represent a vertical component. And for vectors, to differentiate them from points, we're using kind of these angled brackets instead of the round parentheses. A vector is considered in standard position if the initial point is at the origin at 0, 0. And if that's the case, then the components are pretty straightforward and they would match up with an ordered pair, the x, y coordinates that we're used to seeing. If the vector is not in standard position, then finding the magnitude becomes an application of distance formula. So let's see how we would go about using that in an example. So we're looking for component form and the magnitude. I find it helpful to draw a picture of this vector and get a visual of what we're looking at here. So just plotting these points in an XY plane and drawing the directed line segment to represent the vector. In drawing your vector, it's important that your arrow be pointing from the initial point towards the terminal point. Direction is important. Now this vector is not in standard position. We are not starting at 0, 0. So in order to find the first component or the horizontal component, we do have to figure out sort of how far is this vector moving to the left from the initial point to the terminal point. And we can do that by subtracting our two x values of the 2 points that we're given. So we would start with the terminal point and subtract the initial point, starting with just the x values. So in this case, that would be -1 minus 4, which would give us -5. Now for the vertical component, we're going to use the y values, and we are going to subtract them also, starting with the terminal point, subtracting the initial point, this time just the y values. So that's 5 minus the -7, which would give us 12. So component form of this vector is -5, 12. Now finding the magnitude, notation that we use for magnitude has double bars on each side of our vector. And finding the magnitude is just the distance formula. And if you've already found the components, you have done most of the work. So you can find the formula in the book and the slides, but it is just the distance formula. And we've already found the components, so we can just use the components squared. And take the square root of the sum of those. So in this one, we get the square root of 169, which is 13. So magnitude of this vector is 13. Next, let's talk about some vector operations. So we're going to start with scalar multiplication and addition. So multiplying by a scalar, which for us scalars are always going to be real numbers. If it's positive, it's just going to change the magnitude of our vector. So the comparing vector v with the vector 2v, 2v is going to be twice as long. So it's going to change our magnitude and make it twice as long. Both vectors will have the same direction. If we are multiplying by a negative scalar, then that will change the direction. So the direction will be opposite the original vector. So in comparing the vector v with the vector negative v, they will have the same magnitude but opposite directions. To add two vectors geometrically, you would position them head to tail. So you would put the initial point of the second vector at the terminal point of the first vector. And so the sum would be the vector that's formed from the initial point of the first vector and the terminal point of the second vector. So here are the definitions for how to perform these operations algebraically. For addition, you would just add the components, so add each component. And for scalar multiplication, you can think of distributing the scalar throughout the vector. So for example, negative v, that is multiplying negative 1 times our vector v. We would be multiplying negative 1 by each component in the vector. So if we wanted to subtract, remember that subtraction is just addition of the opposite. So we really don't need a new rule for subtraction. Just think of it as adding the opposite of the second vector. So let's do a couple of examples with these operations. So first we've got scalar multiplication. So we are going to multiply 2 by the components of the vector v that were given to us. So we're in a sense just distributing, we're multiplying each component by 2. So we've got negative 4 and 10. Those are the components of the vector 2v. So next we're going to subtract the two vectors. And so if you want to change the second vector and make them all opposite and then add, you can do that. That's just the same as subtracting. So you can just subtract each component. So remember that when you're subtracting a negative, that is the same as adding positive. And 4 minus 5 is the same as 4 plus negative 5. It's just usually easier to add than to subtract. Now let's do a combination of the two things in part C. So we're going to take our vector v and we're going to add it to 2 times w. So not doing anything to v. And we're going to multiply 2 times the components of w. So order of operations still applies here. We still want to do our multiplication before our addition. In the book and the slides, you've got a list of more properties of vector addition and scalar multiplication, and they are associative and commutative. You add the opposite, you get 0. So a lot of the same properties that we're already used to, vector operations would have those also. So next, let's talk about unit vectors. A unit vector would have a magnitude of 1, and it would be in the same direction as a given vector. So in order to find a unit vector, we would divide a vector by its magnitude.
Okay, so we're going to use this definition to find a unit vector for this given vector v. So we just need to take the vector and divide it by its magnitude. Remember that the magnitude is the square root of the horizontal component squared plus the vertical component squared. So for this one, that would be -2 squared plus 5 squared, all into the square root. If you would rather find the magnitude like off to the side in a separate calculation, feel free to do that. And what I get there is the square root of 29. And so what this means, dividing this vector by the square root of 29, is just multiplying it by 1 over the square root of 29. So that's this second part of the notation here. We're just going to split the fraction apart and think of it as multiplication. So this would be like scalar multiplication. And we know that we would just be multiplying by each component. And so that would give us -2 over the square root of 29. With fractions, you just multiply a whole number on the top. Over the square root. Now, if this is a unit vector, the magnitude of this new vector should be 1. So you could check that. If you calculate the magnitude of this vector, it should be exactly 1. Next, we're going to write some vectors in terms of the standard unit vectors. So these two vectors, I and j, are the standard unit vectors. And so I just gives us the, it's a horizontal, and j is a vertical. So we can represent the horizontal and vertical components of any vector in terms of these two. So you'll see them in boldface to let you know they're a vector. Sometimes you see like a little, they call it a hat, but it's just like a little caret, like the caret on the keyboard on top of these vectors. Or I'm going to use the arrow on top like we've been doing for the other vectors. So we can write any vector in terms of the unit vectors, the standard unit vector. We would just take our horizontal component and multiply by this unit vector. And we would take the vertical and multiply it by this. And so we could simply write this as v1 times the unit vector, v1 times the unit vector I plus v2 times the unit vector j. This is called a linear combination of the vectors I and j. So just for a quick example, if we wanted to write a vector as a linear combination, we would just separate the components. So we would have 6 times the unit vector I plus, or you could write it as -2, or we could say plus -2 times the vector j. All right, so next up, let's talk about direction angles. So now we're introducing the thought of this angle. So get back to angles. Let's think about this vector B in this coordinate plane. And let's draw a triangle using its components. This would give me the horizontal component. This side would be V1. The vertical component is V2. And the direction angle is measured counterclockwise, so always the way that we rotate for positive angles. So if we think about our trig function, sine and cosine, sine of this angle theta, based on this triangle, is opposite over hypotenuse. The opposite is V2. The hypotenuse is going to be the magnitude of that vector. So using our notation for magnitude, that will give us sine of this angle theta. Cosine of this angle would be the adjacent side of 1 over the hypotenuse, which is the magnitude. Okay, so the tangent of this angle, we know is sine over cosine. If we were to divide these two expressions that we have for sine and cosine, we've done this many times. Our cube change flip. Our magnitudes would cancel. We would just be left with V2 over V1. So tangent of this angle theta is V2 over V1. We can use that to find theta. So if I have this equation as a tangent of theta, it's V2 over V1, and I want to know what's theta, we can use the inverse of tangent to undo our tangent function, and that will give us theta. So let's do that. All right, so part A, I'm looking for the direction angle of this vector u. This is saying that my vector u as the component, the horizontal component is 3, vertical component is 3. So tangent of my direction angle will be 3 over 3. So tangent of that angle equal to 1. So I'm looking for an angle whose tangent value is 1. We know that one from the unit circle, the point where sine and cosine are equivalent to each other. That happens at 45 degrees. So you could also use tangent inverse on both sides. But our direction angle in part A, just 45 degrees. So pi over 4. In part B, our vector v, can see the components here. It's a positive 3 and a negative 4. To find the direction angle and the tangent of that angle, that's got to be equal to my vertical component over the horizontal. So negative 4 over 3. So this time I am going to use the inverse or arctan. And what I'm going to get here, because this angle, let's draw this vector. Draw this vector on the coordinate plane. Positive 3, 4, this vector in the fourth quadrant. So the angle that we're looking for, we want it to be measured positively. So starting at the x-axis, going counterclockwise. This is the angle that we want. I know that using the inverse of tangent, what I'm going to get is this same angle, but negative. So if I use my calculator to get arctan, I'm not going to call this theta, I'm going to call it theta prime because it's going to end up being a reference angle. But that gives a negative angle. And I'm going to give it in degrees. It's about negative 53.13 degrees. That is not the direction angle. The direction angle should be positive. So I just need to find the angle that's coterminant to negative 53.13. But that's positive in the fourth quadrant. So I'm just going to add 360 to it. Remember, finding coterminant angle theta is negative 53.13 plus 360 degrees, and that comes to about 300 and 3.87 degrees. So this angle looks the same, but it's the one that's measured positively and rotating counterclockwise from the x-axis. So here's our direction.